Welcome to sections 12.10, 12.11, 12.13, and 12.14. Now this is a whole bunch of little sections that are intertwined together, so I'm going to try to cover them in one lecture. In the last lecture, we started talking about the quantum numbers. The quantum numbers are the solution to the Schrödinger equation. The Schrödinger equation is going to go ahead and describe an orbital. That is, it is going to describe a wave, which is what we are envisioning our electrons to be. Now, the quantum numbers tell us characteristics about that wave or that electron. The principal quantum number is going to go ahead and tell us the energy of that electron. So in this diagram, I have n equals 1, 2, and 3, the things that make up the electronic shells of my atom. Now, in each one of these shells are the subshells. The subshells are described by the quantum number L. Now, based on n, I can only have certain values of L. We usually refer to the subshells in their letter designation. So we have S-type orbitals, we have P-type orbitals, and we have D-like orbitals. Now, each one of these subshells have a certain shape. The s orbitals are sphere-like, the p orbitals dumbbell, the d orbitals the clover. Now each one of these orbitals are orientated in space a little differently. So for s orbitals, which are completely symmetric, there's only one orientation. But for p orbitals, there are three orientations, and those have different m sub l values. For the d orbitals, there are 5 orientations, and so there are 5 m sub l values. If we look at this diagram, what you'll see is all these p orbitals have the same energy. If the orbitals have the same energy, we say that they are degenerate. Now, before we move on, there's one more quantum number we should describe, and that is the m sub s quantum number. The idea here is to go ahead and describe a quantum mechanical phenomenon. If I were to go ahead and shoot hydrogen atoms through a magnetic field, something with a north pole and a south pole, what I would see is half the atoms would be deflected up and half the atoms are deflected down. This has to do with the one electron in the hydrogen atom. It is interacting with the magnetic field. We can describe this as the magnetic spin. Now, even though I say the word spin, I'm not saying that the electron is spinning like a top. That would be angular momentum, and there's already a quantum number associated with it. This is a purely quantum mechanical effect and does not have a classical Newtonian analog. What I can say is those electrons that were deflected up had an m sub s value of plus 1/2. For those electrons that were deflected to the bottom, I can say it has an m sub value of minus 1/2. Now, it turns out with 4 quantum numbers, n, l, m sub l, and m sub s, I can fully characterize an electron. So this is going to tell me how the electron is going to behave inside an atom. What you should note is no 2 electrons in an atom can have the same quantum numbers. The reason being is if they had the same quantum numbers, you would be describing the same wave, i.e. the same electron. So to get a distinct electron, one of the 4 of these quantum numbers have to be different. This is called Pauli's exclusion principle. So to summarize everything with our quantum numbers, n is going to tell you the energy of the orbital, L is going to tell you the shape, m sub l is going to tell you the orientation of that shape, and then m sub s is going to tell you if that electron is spin up or spin down. We have restrictions on what n can be, and L is going to be dependent on n. And the restrictions on m sub l is going to go ahead and be dependent on L. Once I have all these ideas, what I can start doing is writing down the electronic configuration, i.e. how each electron in my system is behaving. What I will say is that I have orbitals in my atoms. That is the possible ways that the electron can behave. When I fill an orbital, what I'm saying is that electron adopts the quantum numbers associated with that orbital, and that electron can be found based on those quantum numbers. Now, when I go ahead and put electrons into an atom, we will always go ahead and fill or adopt orbitals with the lowest possible energy. After those orbitals are filled, I can start filling in orbitals at higher energy. What I can do is I can go ahead and do a little thought exercise. This should be the way that my atom is structured with its orbitals, and I can go ahead and do the electronic configuration of hydrogen, helium, and lithium. So let's do the electronic configuration of hydrogen. So hydrogen has one electron. So I'm going to go ahead and put the electron in the lowest orbital possible. So what I'm going to draw is the electron as a half arrow. So this electron can be represented by 4 quantum numbers. Those 4 quantum numbers are N, L, M sub L, and M sub S. So for this one electron, N equals 1, L equals 0, M sub L equals 0, and since I drew the arrow pointed up, I'm going to put plus 1/2. So what I can say is the electronic configuration of hydrogen has the 1s orbital with 1 electron in that 1s orbital. Now let's go ahead and do helium. Helium has 2 electrons. So the first electron that I could do is going to look exactly like hydrogen. And so I'm going to keep it in this blue color. Now I have to put in the second electron. Now the second electron, I'm going to go ahead and try to put it in that 1s orbital. So I can have n equals to 1, L0, M sub L0, but I can't put the electron as spin up because I will have the same set of quantum numbers. And so remember, to have a unique electron, I have to have a difference in one of the 4 quantum numbers. So instead, what I'm going to do is I'm going to draw that second electron spin down. So all my quantum numbers are the same, except I'm going to have minus 1/2 for M sub S. So my electronic configuration for helium, I can write as I have the 1s orbital, and there are 2 electrons in that 1s orbital. Now the next element I can do is I can go ahead and do lithium. Lithium has 3 electrons. Now what you guys can see is that the first electron is just like the hydrogen. The second electron is just like that helium, but now I have a third electron. Now the third electron, what you guys will notice is I can't put it in that 1s orbital. Because if I try to do it, I'll have 1, 0, 0. I can't have plus 1/2. I can't have minus 1/2. So that means the third electron has to go into n equals 2, or the second electronic shell. So I'm going to put a 2 for my n value. Now, according to this diagram, the 2s orbitals and the 2p orbitals are at the same energy level. They are degenerate. However, what experiment shows is that I will always put this third electron in the 2s orbital, meaning I go to L equals 0, and M sub L is going to be 0 as well. I can put a plus 1/2 for my M sub S, and so I can draw the third electron. And so my electronic configuration is going to be 1s2 for the first 2 electrons, and then 2s1 for that third electron. But let's go ahead and talk about why the 2s is preferred over the 2p. The idea behind this has to do with this phenomenon called shielding. So what we can talk about with shielding is first what's called the Z effective. What we have at the center of our atom is our nucleus. It's going to have a positive charge. And so let's say that positive charge is Z. Now, what an electron feels is what's going to be called Z effective. And so if I look at inner electrons, well, there's nothing blocking that inner electron from the nucleus. So the inner electrons, the Z effective, or what it feels, is equivalent to Z. However, if I start looking at outer electrons, what you guys will notice is that these electrons right here are blocked by these inner electrons. These inner electrons are going to start pushing the outer electrons away. What that means is that these inner electrons are shielding those outer electrons. And so what happens is the Z effective for an outer electron is less than the Z, or the real charge of the nucleus. The Z effective for those outer electrons is going to be Z minus the amount of shielding those inner electrons are going to cause. Now, if we look at the probability distribution of a 2p and a 2s electron, what you guys will see is the 2s electron approaches the nucleus very closely. That means there's a good probability of the 2s electrons getting really close to the nucleus, meaning it can shield the 2p electrons. Now the 1s is going to go ahead and shield both the 2p and the 2s, but because of this probability for the 2s to get really close, we say it can penetrate. So in general, the 2s orbital is going to be lower in energy than the 2p orbital because it approaches the nucleus more and is shielded less. Now, this progression happens throughout all the orbitals. An s orbital is going to be lower in energy than a p orbital, which is lower in energy than a d orbital, which is lower in energy than an f orbital. So what I get is a rearrangement of the orbital diagram for my atom. What you guys will see is the 2s is lower than the 2p, and remember, I always fill lowest to highest. And so that's why when we looked at our lithium picture, that third electron preferred to go to the 2s rather than the 2p. Now this brings about a complication. What you guys will see is right around here, we start jumbling where our orbitals are. For example, what you guys will notice is that the 4s is lower in energy than the 3d. What that means is the 4s orbital is filled before the 3d because it is lower in energy. Now there's a couple of ways that you can memorize how to fill out this chart. One way is to do this diagram right here. And the way to do this diagram is you write down your n values, 1, 2, 3, 4, 5, 6, and then you go all the way down. You write all the orbitals available in each one of these shells. So for n equals 1, there's only an s orbital. For n equals 2, s and p. For n equals 3, s, p, and d. Now, once you go ahead and fill out all these lines, you can go ahead, you start from the right-hand corner and work your way diagonally down. So you fill the 1s, and after you fill the 1s, you fill the 2s, the 2p to the 3s, the 3p to the 4s, to the 3d to the 4p to the 5s, and so forth. Now, if you're more mathematically inclined, you guys can use a formula. The way that you figure out which orbital is lower is you can use the simple formula n plus L. Whatever has a lower value is going to be filled first. So if you're trying to figure out which is the lowest energy, the 3p, the 3d, or the 4s, you can go ahead and use this mathematical formula. So in the first one, I have 3 plus 1, which gives me 4. For the second one, I have 3 plus 2, which gives me 5. This is going to be 4 plus 0, or 4. So what I can see here is 5 is the highest number, so it is the highest energy. Next, what I see is that I have a tie between 4s and 3p. If it has the same n plus l, to break the tie, we are always going to put the lower n lower in energy. So in this case, the 4s is going to be in the middle, and the lowest energy is going to be the 3p. And so this is the order. You're going to fill the 3p first, then the 4s, then the 3d orbitals. The last way that you can do it is you can just simply memorize the order in which the diagram is laid out. Do whatever's most comfortable for you, but let's go ahead and practice doing more electronic configurations. Let's do beryllium, boron, and carbon. So I can draw my energy diagram out, and let's go ahead and start with beryllium. So beryllium has 4 electrons. So 1, 2. The third one is going to be just like lithium and goes in the 2s orbital. And then the fourth electron, I'm going to go ahead and pair it up in that 2s orbital. What you guys will notice is every orbital is going to get 2 electrons. So the electronic configuration for beryllium is going to be 1s2, 2s2, because it has 2 electrons in the 1s orbital and 2 electrons in the 2s orbital. Next, let's do boron. Boron has 5 electrons. So I'm going to start from the bottom. 1, 2, 3, 4, and now I've run out of space in the 2s orbital. So the next lowest orbital is the 2p, so I'm going to go ahead and put an electron in the 2p orbital. So its electronic configuration, 1s2, 2s2, 2p1. All right, let's do carbon, 6 electrons. So 1, 2, 3, 4, 5, just like boron, and now I have to put the 6th electron. Now I have a choice. I can go ahead and pair it up like this, or I can put this next electron into an empty orbital. Now what we see experimentally is that this is the configuration we see. We see that the electrons are going to go ahead and spread out in degenerate orbitals. And this is what Hund's rule is going to describe. When you have orbitals that are at the same energy, what we can do is we can go ahead and fill up every degenerate orbital first before we pair it up. Now this should make sense to you guys. Remember, these orbitals right here are describing the location of where those electrons are. And so if I pair them up, that means those electrons are much closer together. And remember, electrons are negatively charged. They want to go ahead and spread out as much as possible before they go into the same location. That's why they will go ahead and adopt orbitals in different orientations to spread themselves out further. So to summarize electronic configuration, first you guys are going to follow what's called the Aufbau principle. That means fill the lowest energy orbitals first. Remember that each orbital gets only 2 electrons because of Pauli's exclusion principle. And finally, Hund's rule tells you that if you have degenerate orbitals, meaning they're at the same energy, you are going to spread them out before pairing them up. You want to maximize the number of unpaired electrons in your system. You can use whatever you guys want to draw your energy diagram. either this way to generate the picture, memorize the picture, or use the formula N plus L to figure out what's the lowest in energy. So why don't we go ahead and try a quiz question out. Tell me what the electronic configuration of chloride is. So this is an anion. I want to negatively charge chlorine. All right, gentle people, chlorine has 17 electrons. But if I make the chloride ion, I have 18 electrons. So let's go ahead and fill 18 electrons into my energy diagram. So I'm going to start with Aufbau's principle and start from the bottom. I'm going to use Pauli's exclusion principle and only put 2 electrons in each orbital. So I got my first 4. When I get to the 2p, I'm going to follow Hund's rule. First, I'm going to spread them out. And then after I spread them out, I'm going to go ahead and pair them up. So I've got 10 electrons, 11, 12, 13, 14, 15, 16, 17, and 18 electrons. So what I can say is that I've got 1s squared, 2s squared, 2p with 6 electrons, 3s with 2 electrons, and finally my 3p is fully filled with 6 electrons. And so this should have been choice D for you all. Let's go ahead and take a look at some electronic configurations, because what you'll notice is that a lot of these electronic configurations become very tedious to write. So what you'll notice is the noble gas right here, neon. And if I were to do its electronic configuration, 1s2, 2s2, 2p6, or if I want to draw it in the box diagram format, you can see it like so. What you will notice is that neon has all its shells filled. The 1s is completely filled, and the 2 is going to be completely filled as well. If I go ahead and look at sodium, I can say it's 1s2, 2s2, 2p6, 3s1. What I can see is n equals 1 and n equals 2. They are filled, but then I don't fill my highest shell. So what I can do is I can use a shortcut. I will see that every noble gas is going to have its shell full. If the noble gases go ahead and represent a full shell, and then the outer shells of all the other elements are unfilled, what I can do is I can describe the inner electrons in terms of a noble gas. What I mean by that is if I look at the inner electrons of sodium, I can see it exactly matches that of neon. And I can split up my electrons into 2 categories. The electrons that are on the outside, which are going to be called the valence electrons. For anything that's not a noble gas, my valence shell is not going to be filled. The inner electrons are going to be core electrons. The core electrons are going to be in shells which are completely filled. And so what I can do is I can describe my core electrons in terms of a noble gas. So instead of writing sodium like this, I can say that sodium has a neon core, and then on the outside, it has 1 electron in the 3s orbital. And when I say it has a neon core, I'm saying this is the inside configuration. You guys can test yourself with calcium. Calcium, what you will note, is the core electrons are the same as argon, the noble gas that immediately precedes it. Calcium has 2 more electrons than argon, and those 2 electrons go into the 4s orbitals. So this is the electronic configuration of calcium. We can continue our discussion on these electronic configuration by looking at the transition metals. The element after calcium is scandinavium, Sc. What you guys will see is its core is filled and is similar to argon. This element has 3 more electrons than argon. So that means it has an argon core. The first 2 electrons are going to go into the 4s orbital, and then the third electron is going to go into the next highest orbital, which is 3d. So its electronic configuration is argon 3d1, 4s2. Sometimes you will see that they switch places with the 4s and the 3d, and so they might write it as argon 4s2, 3d1. Either one should be fine. Now, what you guys will notice is we can continue this progression down the transition metals, filling up 10 electrons once we get to zinc. Now, what you will see is that this matches the periodic table. The periodic table we told you was based on reactivity. That reactivity is actually based on the electronic configuration. And so in reality, the periodic table is arranged based on electronic configuration. You have n equals 1, and there's only the s orbitals. So only 2 elements are up on the top. You have n equals 2, and then you have the s orbitals, which can only accommodate 2 electrons, and then the p orbitals, which can accommodate 6 electrons. So that's why the second row in the periodic table is 2 elements, followed by 6 elements on the other side. Same thing happens with n equals 3, 2, and 6. Then once you start getting to the 4th row, you start to introduce the d orbitals. And what you'll notice is that I can put 10 electrons in the d orbitals, and that's why you have 10 transition metals going across. You'll also note that those elements, the lanthanides and the actinides on the bottom, there are 14 across, and that's because there are 14 F electrons. So if you look at the periodic table, you can determine the electronic configuration. Just figure out which row you're at. This is going to be your S block, so that means your valence electrons are going to be in an S orbital. This is the P block, that means your valence electrons are going to be in the p orbital. The D block with the valence electrons in the d orbitals. Now just be careful, the d orbitals are offset by 1, meaning 3d starts in row number 4. The same can be said with our f orbitals. Our f orbitals, they start to come here, so they are on the 6th row, and so they are offset by 2. Now I should note there are 2 exceptions to the rule that always appear on standardized tests, and that is chromium and copper. So chromium appears here on the periodic table. So if you were to do its electronic configuration, you would say that it has an argon core, 1, 2, so 4s2, 1, 2, 3, and 4. So 3d4. That's normally how you would do most transition metals. It turns out that chromium is an exception. Instead of being this configuration here, it turns out it's more stable if one of these s electrons gets promoted. And so what happens is that chromium becomes argon core 4s1 3d5. This is called the half-filled stability. And so chromium is one of these elements that does this exception, and you're just going to have to memorize that it does. The other exception is copper. If copper were following the rules, it would be argon core 4s2 3d9. But it turns out it does the same thing and promotes 1 electron to get that s orbital half filled. So its true configuration is argon core 4s1 3d10. So these are the only two exceptions that I want you to note. Well, Chem 1A, I hope that made sense, and remember to stay safe.